I'll be talking we'll be talking about shared control for human interaction from an energy-based perspective. I will try to highlight what are the main control challenges for shared control, in my opinion, and I will try to propose a solution to you. So let's start from the motivation, well, very broadly from a motivation. So interaction is super mega important in our life. Basically, it's the first thing that we do as a child. And because why that? Because it's touch is a very rich information, and we look for touch every time, and it's very easy to perform. Sometimes we cannot reach everything, and we need help. Okay, well, robotics has provided an help for us to reach the unreachable since the very early days. So through a teleoperation architecture, the human as a master teleoperates a robot as a slave through a bilateral control architecture, okay? But, well, in standard teleoperation, the slave is really a slave. Basically, the master is a sort of puppeteer that decides completely the motions of the robot. So in terms of authority, well, we have to say that the human is in full authority and the robot basically does nothing but replicating the human commands. Of course, things are getting more complicated, and luckily robots are getting better and better. So today we can aim at facing more complex teleoperation tasks, like for example, exploring an area using more than one robot, like for example here, several quadrotors. And we can delegate to robots a little bit of autonomy, okay, because robots can afford that. Okay, so overall is more complexity, that can be complexity of the task and complexity of the robotic system we want to teleoperate. Consider also, for example, this scenario. Well, I want to put a piece on this board using a visual feedback. Well, everything is fine as long as the robot is not close to the board. Then I cannot see anymore the exact position of the end effector, and therefore I would like the robot to take care of the last step. So it's important that the robot gains some autonomy. So more complexity, more autonomy, less human. Still human is important, but the robot can do something. So this is very nice, thinking about giving some authority to the robot, thinking about asking the robot to do something by itself and to, let's say, interact in a very nice, smooth, and efficient and effective way with the human. But there are a lot of problems behind this desire. First, it's dynamic authority allocation, which means from a control point of view that you have an entity that changes its authority dynamically. So the dynamics that is injected into the system changes over time, okay? Second, there is a variable interplay among several dynamical systems that may be poorly known. Like, for example, the human, well, it's very hard to build a reliable model of the human that is good all the time. Yeah, there's a lot of work on that, but still, well, the human behavior is poorly known, but still the human is not a static system. The human is a dynamic system that interacts with all the rest of the system. And then there is also a further problem. Right now we have seen amazing advances in artificial intelligence, and there are wonderful ways of describing tasks like linear temporal logics and other beautiful settings. And perception is becoming more and more informative and more reliable. So there are all these external high-level information that are injected into the overall shared control system that again, produce dynamic changes in the architecture. And if you're familiar with control, well, all these dynamic changes will have to be carefully addressed because they can very easily cause instability, okay? And so dangerous behavior for the human. So the question I would like to discuss with you today is, what is the control structure that shared autonomy should leverage? Okay, so it's very nice to have high-level description. It's very nice to decide who has to do what depending on what happens on the desire of the human. But below, what's the control structure that has to take care about keeping everything to be working in a sound and safe way. So, well, I believe that we should not forget teleoperation, which is in some sense the first human-robot interaction system that has been developed in robotics. Okay, and over the years, several major understanding of the human-robot interaction have been made. Okay, so for example, since the early 80s, well, there have been many experiments showing that actually force feedback is very useful for task awareness. Second, late 80s, early 90s, well, it has become clear, I'm thinking about Anderson Spong, Niemeyer, but also the work of Hogan about impedance control, that if we want to have a sound and safe interaction, we need to guarantee a sort of robust stability. So we need to guarantee that our system is stable, both in free motion without interacting with anything and while interacting with the human or with the environment. So passivity has been shown to be at the moment one of the best tools for ensuring this kind of robust stability. Then more recently, we have seen that sticking to physics limits performance. Since, well, I would say 10 years ago, well, passivity-based control was based on reproducing a controller that was mimicking a physical dynamics like mass spring dampers or a random interconnection of mass spring dampers according to the controller you want to implement. Well, but sticking to physics limits performance. So what do you achieve is safety, stability, but bad performances and not so flexible performances. And so many works have been done for trying to free passivity and to allow to implement more flexible controllers, passivity-based controller. So Don Jun Lee's proposed the PSPM, G1 Liu proposed the time domain passivity-based approach, and we proposed the energy tanks for the two-layer architecture in bilateral teleoperation. So today I would like to show how to dynamically handle passivity in order to get something that is still robustly stable, but also flexible. So this is the energy-based shared control architecture that we are proposing. So in our view, shared control should be robustly stable. So passivity may be a tool for, let's say, guaranteeing this robust stability. So guaranteeing that the overall system is passive allows us to guarantee that the overall system is stable. So flexibility. So I don't want to be constrained to implement a certain physical dynamics, so mass spring damper or a PD with a fixed stiffness or whatever. Okay, why that? Because it's in contrast, it's in sharp contrast with shared control. In shared control, we want the system to be active and to be reactive. So if the environment I'm interacting with changes, if the conditions I'm working with the robot with change, I want the authority to change. And of course, I want awareness. The human should be there and the human should be aware of what's going on. And taking what has been known in telerobotics since decades now, well, I want to implement a proper force feedback to the human. So this is the overall architecture. I leverage on a master-slave architecture, so I still have a master robot, a slave robot, okay? But the link is milder with respect to standard teleoperation. Why that? Because I have a local control structure that determines the autonomy of the slave, of the robot, okay? I don't like the word slave, but anyway, okay? Of the remote robot, okay? So the local control allows, so the slave is controlled using these two controllers, the human commands and the local control. And the overall system has to interact with the environment. And how do we decide the local control? The local control is not fixed. It depends on this red box, which is the authority allocation or shared control block, where, well, I want all the high-level data that I collect. I want to process them using some very nice high-level architecture. I don't want to understand, well, my robot has is torque control, my robot is, well, I don't know. I don't want to deal with low-level details. The authority allocation block, in my view, is something that takes into account things at the task level. Well, do this, do that. So how can we implement this in a passive, flexible, and with a good force feedback? So we're going to use using energy tanks. So shortly, what is an energy tank? An energy tank is a dynamical system that is slightly more than a simple integrator, okay? Basically, you can connect an energy tank to any passive system, and the energy tank collects the power dissipated by the system, okay? And the power dissipated is stored in the tank, okay? And it's possible to reuse the energy dissipated that otherwise would be wasted for implementing a desired input for the system. This interconnection, okay, simply pumps out the energy from the tank and puts it in the system, into the system in order to implement the desired interconnection. Notice that the interconnection is asymptotic, is power preserving, which means that energy is exchanged between the tank and the system. So I'm not proving anything here, but just the intuition, okay? I store the dissipated power and I use the power and I feed back the power to the system. So there's no energy production, so it should be intuitive that the system is passive. Thanks to this interconnection, well, I can always implement the desired value by setting F is equal to W, and W is a parameter of the interconnection. So I can tune the interconnection in order to implement the desired force, in this case, on the system. So I can freely use all the energy that is in the tank. I'm not constrained anymore to springs, mass. I have a reservoir of energy, and I can use that energy for doing whatever I want, okay? As long as everything is well defined, namely as long as x of t is different from 0, which means as long as I have some energy into the tank. Okay, so consider the problem of teleoperation of a multi-robot system. So what was one of the early ideas we had? So also in collaboration with Antonio and with Paolo, well, some years ago now, we developed authority through physics. So the human cannot teleoperate more than one robot at a time. And so we decided to interconnect the robots through springs, okay? So nonlinear springs characterized by a specific storage functions, a specific potential energy. Well, to make a long story short, this nonlinear energy guarantees a cohesive behavior, so all the robots stick together, let's say, collision avoidance, and by using a slightly more complicated spring, also connectivity maintenance. So at the end of the day, we made of a set of robots as a unique virtual physical system that is robustly stable because everything is passive with respect to this port, okay? But the thing is that the system as it is super simple, but not so flexible. Why that? Because the dynamic behavior is fixed. Once I interconnect the two agents using a spring, well, that's the spring. The kind of dynamic behavior is determined by the spring. And therefore, I have a fixed model of interaction because, of course, the stiffness the agents are interconnected with determines the way the overall multi-robot system interacts with the environment. And so, what's the problem? If I want to change it, well, then I have a sort of hybrid system, and then I have all the problems of handling hybrid dynamics. So what's the problem for that? The problem is due to the fact that I reproduce passivity using physics, because I know that physical systems are passive systems. But passivity is more. Passivity does not require that the controller has to mimic a physical behavior. Passivity requires that the controllers are, that the overall system has a certain energetic behavior. So we should not embody passivity, but we should consider passivity for what it is, namely energy flows. Okay, so also in the work we made with Antonio and Paolo, we introduced energy tank for being able to reproduce some more flexibility using split and join maneuvers, for example, for quadrotors. Here, what I would like to propose is a more general thing. So instead of using a spring, just interconnect two quadrotors, two agents. Okay, quadrotors is just an example, two agents using this sort of tank-based interconnection. Okay, what is a tank-based interconnection? It's pure energy. It's an interconnection made of pure energy. So consider a pair of robots. Okay, so we have that the two robots share this interconnection structure, which is made up of an energy tank and two modulating matrix. Well, actually, it's one modulating matrix, first taken with the transpose and then without the transpose. So what happens? Suppose that I can measure the velocity and I want to reproduce a certain force that is governing the interaction between the two robots. Okay, what happens with this kind of structure? Basically nothing. Well, nothing in practice, but let's see. So I have two quadrotors. Suppose that the two agents are passive. So I have that, well, the two agents are satisfying this power balance, this energy balance. Okay, so the energy is stored in the tank, and by properly choosing the power, the modulating matrix A of t, I can arbitrarily set the interconnection force as long as there is some energy into the tank. You see, well, basically what happens, I have no physical dynamics there. I have just a flow of energy, okay? And the computations are very simple. You can show that everything is passive. So the two robots together with this interconnection, with this energy-based interconnection is passive. So what did I do now? Well, I just coupled from an energetic point of view using the energy tank two robots, okay? And I ensure that as long as there is some energy into the tank, so as long as this interconnection is well defined, well, the overall system is passive. What did I create? Did I create a specific interconnection between the two robots? No, not at all. I just enabled the creation of a specific interconnection. I just energetically coupled the robots in order to guarantee that the overall interconnection is passive. So it is necessary to guarantee that the energy stored in the tank is greater than zero, and energy can be harvested by augmenting the damping. But the thing that I proved is that the two agents interconnected by the tank-based generalized interconnection, well, are passive. So what happens now? How do I choose how to use the energy stored in the tank? Well, we can put an optimization block over this interconnection, okay, and an extra block that determines, according to high-level decision makers, okay, what kind of coupling should I apply? So I have a desired interconnection, which is the pair of forces, the one that should be applied to robot I and the one that should be applied to robot J. And I have an optimization problem. The optimization problem takes as an input the desired interconnection and the energy available for implementing the desired interconnection. What you get is that you can use the energy in the tank by solving this optimization problem, okay? Which is a convex optimization problem in discrete form. And what is this telling you? Well, it's telling you, very, very informally, do whatever you want as long as you leave some energy into the tank. Because if you leave some energy into the tank, I guarantee that you are passive, okay? And so what you have is that I try to find the best passive interconnection for my pair of robots. So I have the tank that captures energy and that unconstrains completely the kind of dynamic behavior you can implement with your system. And the optimization problem modulates the matrices A that you have seen in the previous slides for tuning the way, for modulating the use of energy and implementing the desired interconnection. And everything is easy from a computational point of view because everything is complex. So is it well posed? Well, yes, because it turns out that if you implement any passive interconnection, you never deplete the tank. And therefore, it's a generalization of a standard passive interconnection. Standard in the sense that you implement a passive interconnection by reproducing the physical dynamics. More, if you have some energy, more, you can also implement some non-passive interconnection. So again, this structure allows you to guarantee passivity and therefore robust stability for your slave. So the structure you can use for teleoperation of multi-robot system is, again, an extra block, which is high-level authority allocation, the one that decides what the interconnection should be, what the dynamic behavior should be, according to perception, decision-making, and whatever. Okay, then I have the desired interconnection, the optimization, the tanks, and at the end of the day, I implement something that is provably robustly stable. Okay, and this is very cool because it allows me to safely interact with the robot. And it turns out that the control structure is very simple because the dynamics of the overall system is augmented simply by these two terms, which represent the coupling between the tanks and the dynamics of the agents. And it works for general dynamics. So you see f of x is whatever, as long as it's passive. So the change of perspective here with respect to standard passivity-based control is not, well, I design in order to be sure that I will be always passive, but to see passivity passivity as a constraint. I do whatever I want, but I take care of an important constraint. I want to be robustly stable, and therefore I enforce passivity for achieving that. So this is a simple experiment. So increasing the rest length of the spring is a simple change of coupling, but it's something that requires energy. Okay, you see, sometimes the change is allowed here because I have some energy into the tank, and in order to implement the change of rest length between the springs, I exploit the energy stored in the tank. Some variations also induce, they also produce a decrease of energy in the tank. Sorry. So should be an experiment here. Yeah. So we made an experiment with 2 mobile robots. And you see the robot moves and they store energy into the tank because of their friction. And decrease of rest length is dissipative in this case, and the energy dissipated is into the tank. And the augmentation of the rest length decreased the energy into the tank because in that case, energy is required. So what can we do for awareness? So how can we teleoperate the multi-robot system? So we have a multi-robot system. This is coupled using energy tanks, so it can reproduce a very flexible behavior. And I can teleoperate the system by teleoperating a leader. This is a standard, I would say now, interconnection. So I have that the velocity and the position-like variable R are joined using this, well, basically a damper. Okay. And it's easy to see that the overall system is passive, okay? So it can safely be used by the robot, by the human, and the delay can be handled using two-layer approach, for example. But there is still a problem that we should consider. So do you remember I mentioned that awareness, and so a proper force feedback should be provided to the user. And so I would like to have a good force feedback. Using standard passivity-based control, you're ensured about steady state performance. So at steady state, you have a very good force feedback. But at the end of the day, there are many tasks where transients are more important than steady state. Try to play piano in steady state is very bad. You don't want to do that. So the bad thing using multi-robot teleoperation is that the user always feels the fleet, okay? And so, for example, if you model agents using as a point mass, well, this is what the user feels all the time. It would like to feel the force with the external force exchanged with the environment, but it feels this, okay? So again, why don't using the slave authority for shaping the force feedback? Try to speed up. So the idea is, can I change? Can I keep the kind of scale, the kind of interconnection decided by the slave, but scaling it in order to make the performance better at in terms of force feedback provided to the master? Well, turns out that given a desired force feedback at the master, I can tune using proper time varying gains and exploiting energy tanks. Again, I can tune the interconnection of the leader with the other robots in order to maximize, to minimize the distance between the desired force and the force that is really fed back to the user. And so again, it's a super simple optimization problem. So convex with super simple constraints. So it's convex quadratic optimization, neighboring coupling, so it can be implemented in a decentralized way. And again, preserves passivity because the tanks allow to enforce passivity as a constraint. Passivity is always a constraint. Okay. And so this is a simple example we made well a couple of years ago. So you see, without scaling, the distance between the desired force feedback and the real force feedback is of the order of tens, okay? While using the scaling, well, we have that the desired force is very close, the real force feedback is very close to the desired one. Okay, I'll be very quick on these two applications. In this application, we decided to switch between autonomy and teleoperation. So suppose you have a fleet of drones exploring an area, but and in order to keep a cohesive behavior, we have, for example, that the fleet enforces a certain topological property, like, for example, connectivity. But at a certain point, this connectivity may also be too rigid, and it may prevent some of the agents to explore some areas. So the idea is, can the user take a portion of the fleet and teleoperate it? But at the same time, I don't want the robot to be away for too much time. And I would like to enforce a force feedback that calls back the robot to the team after some time, okay, or given some conditions, okay? So we implemented this kind of force feedback, which is non-passive because the potential that is necessary for implementing it is time varying, and time varying potentials are injecting energy into the system. So we plug this into this pipeline of control, and what we have is that everything is passive. Okay, you can see much more on this on this paper that has been presented at the conference. The presentation should be still there, and maybe okay. This is a simulation of the environment that has to be explored. You have the quadrotor that is constrained to stay close to its mobile robot, this docking station. Okay, so after a while that the robot is unconstrained, a potential is activated, and the potential is time varying in the sense that it attracts more and more back to the docking station, the quadrotor. And we have implemented this potential in a teleoperation framework. So we have that our robot, our quadrotor now is in teleoperation, so the user can freely take it to explore some, I don't know, environment. And after a while, you see, you have a peak of force that tells the robot, hey, you've been away too much time, come back to us. Otherwise, well, battery is low or something like that. And this is done in a passive way and in a very robustly stable way. I can take the robot here while the overall fleet couldn't even enter here, and I implement the force feedback using the energy in the tank. Okay, time is passing. Okay, one word on this. We have, of course, we have used energy tanks because, well, to us it's a very nice tool. But we have done some work also on this kind of architecture, exploiting time domain passivity approach together in a collaboration with DLR. And the thing here is that the authority control is connected to an authority allocation module, and the dynamics of the switched authority was pacified by the passivity, by the time domain passivity control. So the scenario is the one that I described earlier. So I have that the perception system is detecting the area that needs to be operated, and the bigger the covariance is about the estimation, the more authority is given to the robot. Okay, and this is a short movie of that. But the architecture is very, very simple, and it's more or less the same. The only thing is that we replaced, energy tanks with time domain passivity approach. The video is very nice, and would be nice if you could see it. I don't know why it doesn't work, but you can find the full presentation of the work in a paper we presented on Wednesday, D21. Okay. Oops, here it is. Okay, so let me go to my conclusions. Shared authority is possible now, and as we have seen the whole day, and it's actually necessary for mastering complexity. So it's nice to have high-level logic, but we should not forget about the low-level control that must ensure robust stability and usability for the user. Energy-based shared control is a possibility, and you can use your favorite dynamic energy handling strategy, tanks, time domain passivity approach, or whatever. Okay. What we are trying to do now is to extend this architecture also to, we did already something, to human-robot collaboration, because at the end of the day, human-robot collaboration is a sort of teleoperation, okay? Teleoperation, in general, is a coordination between a human and a robot. So this kind of architecture is actually fitting also with human-robot interaction, but this is, yeah, work in progress. Okay. Thanks. This concludes my presentation, and thanks a lot for listening. And if you have any questions, I'll be glad to answer.
Thank you, Cristian, for the very interesting talk. So you have a question from the audience. The question is from Lilia. She's asking, to what extent does this framework support non-physical interaction at much higher level?
So I was fast on that, but in the work we did together with DLR, can you still see my slides? No.
Yes. Yeah.
Okay. So this is the environment. This is a dynamical system that is interacting with the rest of the system. So as long as the entity is interacting in terms of using the same ports, like for example here for velocity and forces, well, everything can be handled. So you can pacify also the interaction with non-physical entities. I'm not sure about the performance to get. It may happen that where you don't have exactly the desired behavior. But what is important, what may be interesting is, still work in progress, is not to consider only passivity, but to put into the optimization problem also a constraint on the desired behavior.
Yeah, that sounds interesting.
Yeah.
All right. I have other questions actually, but we are running a little bit late, so I'd like to move to the next speaker. I thank you again for the presentation.
Thank you.